Hello, my name is Shomodip, and in this seminar presentation, I will discuss about synaptic devices for neuromorphic computing. So let's get started. So let's start with what is neuromorphic computing. Neuromorphic computing is implementation of biological neural networks in analog or digital circuits. In simple terms, it is mimicking a biological brain. While our current modern day computers are ideal for solving structured problems, one of the limiting factors in their architecture is that computation and storage are done in two different units, which communicates via the data bus. In neuromorphic computing, the storage and computations are combined in a single unit, allowing massive parallelism and solving problems efficiently where both the inputs and outputs are often imprecisely specified. A recent face-off happened in 2011 in the reality show Jeopardy, where the supercomputer IBM Watson was held against two innocent human beings. They were given tasks mainly based on voice recognition, natural language processing, and information retrieval. While IBM Watson won by a whopping 40-fold difference in reaction time, there was certain information that we need to consider. IBM Watson has 2,880 computer cores that takes up a space equivalent to 10 refrigerators. It also requires 80 kilowatt of power and 20 tons of AC cooling. On the other hand, those innocent human brains requires only 10 watt of power, similar to a light bulb, and takes up space equal to a large soda bottle. Therefore, biological brains are the clear winner here, considering the computation per unit volume and computation per unit power consumed. The computational unit of a biological brain is neuron. Information in brain is processed in form of spikes. A neuron receives spikes from other neurons via dendrites. The received spikes are accumulated or summed up in axon. If the if the amplitude of the resulting spike is greater than a predefined threshold, the neuron fires its own spike or action potential. From now on, we will call it AP. Otherwise, the neuron will maintain its rest membrane potential, which is about minus 70 millivolts. Thus, neuron acts as the logical unit in the brain. The AP is transmitted to the next neurons via synapse. Synapse helps in transmitting the APs from one neuron to the other. The AP opens the calcium channel in the first neuron, thereby allowing calcium ion influx. This triggers the synaptic vesicles to release neurotransmitters in the synaptic cleft. The neurotransmitters open the ion channels of the second neuron, causing ion influx in its dendron. As more and more ion enters, the membrane potential of the neuron increases or decreases according to the type of ions entering. In this way, the spike from the first neuron is transmitted to the second neuron. One thing to notice here is that the magnitude of the action potential received by the second neuron will depend on the synaptic weight or conductivity. In fact, synapse has the ability to modulate its strength according to the neuronal activity going around it. This phenomenon is known as synaptic plasticity, and it is the basis of learning and memory in biological. One important type of synaptic plasticity is spike timing dependent plasticity, or STDP. Consider the two neuron system in the top figure firing spikes at different times. If the pre-spike precedes the post-spike, the synapse potentiates or its conductivity increases. Again, if the post-spike precedes the pre-spike, the synapse depresses or its conductivity decreases. This phenomenon is also called the Hebbian learning rule. Hebbian rule has four forms as given in the figure above. The first one is the anti-symmetric Hebbian rule, as explained just now. The second one is anti-symmetric anti-Hebbian rule, just the opposite of the first one. The below two are the symmetric Hebbian and the symmetric anti-Hebbian rules. Notice that in all the four cases, the synaptic weight is maximum when the time difference is zero. That is, when the neurons are firing synchronously. In other words, we can say that neurons that fire together wire together. A basic unit of neuromorphic computer will mimic all the functionalities of a neuron. The dendrites can be modeled as simple wires to receive the signals. The axon can be modeled as with an adder to integrate all the incoming signals along with a conditional spike generator. The synapse, however, requires a special device to emulate all its functionalities. A synaptic device should mimic the synaptic functions efficiently, like STDP, spike rate dependent plasticities, long-term potentiation, and short-term potentiation. They should be very small and low power consuming. Different non-volatile memory technologies have been reported which have successfully emulated the synaptic functions and can also be fabricated at nanoscale. We will restrict our discussion here to two emerging memory technologies which can efficiently perform the synaptic functions, memristor devices and mem transistor devices. A memristor device can be broadly defined as any two-terminal black box that exhibits a pinch hysteresis loop in its current voltage curve when driven by a periodic stimulation of voltage or current. A memristor operates according to reversible resistive switching behavior stimulated by an external electric field. If you notice the IV characteristic above, there are two slopes corresponding to high resistance state and low resistance state. A memristor exhibits memory operation by transiting by transiting between these two states. A promising material for memristors is organic halide perovskite or OHPs. Due to low activation energy, the halide ions in the material participate in ionic migration in presence of an external field. This ionic migration allows the pinch hysteresis behavior of a memristor. OHPs are semiconductors capable of both ionic and electronic conductivities. Additionally, it shows high photoconductivity which can be used to realize optically stimulated neural networks. The memristive behavior is mainly because of the iodine ion vacancy migration under an external bias. When a bias is applied, the iodine ion vacancies drifts, forming a bridge between the two electrodes. This bridge is conductive in nature due to trap-to-trap hopping mechanism. If the bias polarity is reversed, the vacancies recombine with iodine ions and the conductive filament disrupts, thereby resetting the device. If the electrodes are made of active metals like silver in this case, then those ions will also form a double conducting filament. Charge trapping or detrapping is also partially responsible for the memristive action here. On application of a bias, the Schottky barrier in the metal semiconductor junction lowers, promoting hole injection from the metals and trapping at the interface. This shifts the device to a low resistive state. On reversing the polarity, the Schottky barrier becomes higher, the hole retracts, and the device again shifts to high resistive state. By applying different pulses at the two electrodes of the memristor, all the four forms of Hebbian rule can be realized in a memristor, thereby emulating the STDP or spike timing dependent plasticity of synapse in this kind of devices. While memristor can be useful in synaptic devices, a multi-terminal device like MEM transistor is desirable to realize heterosynaptic plasticity in a complex neural network. MEM transistors are similar to memristor with an additional gate electrode to modulate the hysteretic current. The function of a MEM transistor is similar to a memristor with a pinch hysteresis in the IV curve and a low resistance state to high resistance state transitions. The additional gate voltage is used to control the current through the device as shown in the figure here. Or sorry, here. Yeah, sorry. MEM this kind of the control of the modulation in the current occurs because the gate voltage introduces an additional electric field in the device which modulates the charge carrier concentration inside the device, thereby changing its conductivity. MEM transistors could be particularly useful in realizing neuromodulation. Please look at the figure on the left side. Here, a third object in the synapse, could be a third neuron, is emitting neurotransmitters, thereby altering the synaptic weight. Since OHPs are good photoconductors, light can be used as forced stimulation to this device as well. This can be useful to realize retinal synapses in our eyes. If you look at the first curve, the EPSC or excitatory postsynaptic current shows both long-term potentiation and long-term depression in presence of negative and positive gate pulses. The curve just below shows that the EPSC saturates faster in presence of light and gate field, which represents the conversion from short-term potentiation to long-term potentiation, thereby mimicking the function of a neuromodulator. While OHPs are great materials for memories, a comprehensive understanding of ion migration mechanism is still a research in progress. OHPs have less stability under humid conditions and a good environmental stability is needed for practical application. Lastly, even though remarkable progress has been made in terms of synaptic devices, the implementation of neuromorphic network is still an enormous challenge which causes no clear definition of low energy consumption. Well, that is the end of my presentation. I hope you liked it. Thank you for watching. Have a great day.